Hi there, welcome to this video on graphing cube root functions via transformations for accelerated math 3. What we're going to do today is look at the cube root function and then go ahead and graph different functions via the transformations that are given. Now, for some prior knowledge, here we have the general form of the cube root functions. It is f of x is equal to a times the cubic root of x minus h plus k. Now, in this time we have a parameter of a, but it is also possible to have a parameter of b. So here's another general form of the function g of x equals the cubic root of 1 over b times x minus h plus k. So in these forms, what we're given are a or 1 over b values along with h and k values. Now remember, your a parameter and your 1 over b parameter cause either vertical stretch or compression or reflection for a parameter of a, and then also horizontal stretch or compression for a parameter of b, along with reflection. And then our h and our k values really translate a function. H values can move a function left or right, and your k values will move them up or down, okay? Please take a moment. You can pause this presentation and go ahead and review these if you need to. So what we're going to do is we're going to look at some transformed functions and then just identify the effects on the graph, okay? And this should really be prior knowledge just with a new type of function. So step one, what I'm going to go ahead and do is I want to identify my parameters. So you can see here we have an a value of -3/5. We have a h value of 4. And remember, the h value is always opposite. Okay, so h is always opposite. And then we have a k value here, which is +5. Okay, so what are the effects on our function g of x? So what we're going to go ahead and do is we're going to say the effects on the function g of x include, so I have a negative, right? So that's going to give me x axis reflection. Okay. Vertical, well, my a value is less than 1, so that's going to be a vertical compression by a factor of 3/5. Okay, and then what else is happening? And a translation. Okay, well, h is 4, so 4 units. It's positive, so that's going to be 4 units right. And our k value is 5, so that's going to be 5 units down. And 5 units down. Okay, so I went ahead and I've identified the effects on the graph based upon the transformation parameters given. Let's go ahead and look at another example here. Again, the first step, I always identify, okay, what is given to me. And this time I don't have an a value, but I have a 1 over b value given. Okay, so 1 over b is equal to -1/5, which this means that b is equal to -5. So I have a b value that is -5. We have an h value. Remember, h is always opposite, so h is -7. And our k value is -2. Okay, so step 2, I'm going to go ahead and just describe the effects of the function. And let me go ahead and zoom over. So I can say the effects on the function g of x include, so remember a b value is a horizontal effect. So I'm going to have a horizontal reflection. So horizontal reflection, or a y-axis reflection is another way of saying it. Okay, horizontal stretch by a factor of 5. Remember, we don't include the negative. The factor is 5. Okay. And a translation. So again, now I'm going to describe my translations. A translation of, and I'll do the h value. H is negative, so we are going 7 units left. So again, I don't include the negative. The direction is included with the left. And then as far as the down, and we can say, and 2 units down. Okay, again, I don't include -2, it's just 2 units down. Okay, so that's transformations. That's going to be a part of what we're doing today in our lesson. We're going to go ahead and graph these, based upon these transformations and kind of how they affect our parent function. So let's review the cube root parent function, and that's important. So what you're looking at here is the cube root parent function, and symbolically or algebraically it is represented as f of x is equal to the cubic root of x. That's your parent function, okay? What I like to call the OG, the original graph. Get it? OG. Okay, so since the cube root of a negative real number is a negative real number, there is no need to restrict the domain. So this is different than the square root. The square root, I can't have negative values in my radicand because that produces imaginary values. With the cube root, we don't have to worry about that, okay? So that's good news. All right, let's go ahead and talk about our parent function, the cube root parent function. So if this is our function here, f of x equals the cubic root of x, what happens if I plug in negative 8? I don't know why. Awesome, ugly -8. -8. Well, when I plug in -8, the cubic root of -8 is -2. Okay, so I plug in -8, I get out -2. Next, I'm going to plug in -1. Well, when I plug in -1, the cube root of -1 is -1. Okay, well, when I plug in 0, the cube root of 0 is 0. When I plug in 1, the cube root of 1 is 1. And when I plug in 8, the cube root of 8 is +2. I'm not sure why there's a negative there. Fix that on your notes if yours says negative. So it'd be +2. So I have this point. Now, why am I plugging in those random x's? Well, because you can take a look at the outputs. The outputs are nice, neat numbers, and really these points should be familiar to you. These are the inverse points of your cubic functions. Your cubic functions, right, had the same exact parent function points, just switched, which is what we expect from inverse functions. Okay. Note the domain is all real numbers, I can plug in anything from positive infinity to, or sorry, from negative infinity to positive infinity. And that's good news. Makes our lives easier. I don't have to worry about, okay, what's going in. The range is going to be the same values, everything from negative infinity to positive infinity. Okay, so that's some important note. And then if we're talking about end behavior, we have 2 types of end behavior. Over here to the left, our function naturally is going down. So if I plug in negative infinity into my function, I tend to get a negative infinity out. Okay, so here is your end behavior as x goes to negative infinity. The function values are going to negative infinity, the y values. Okay, and then similarly, if I plug in positive infinity into my function, as my x values grow and grow and grow and grow unbounded, the function values increase unbounded as well. So there is your end behavior. In these examples, we're going to be asked to state domain and range as well as the end behavior. Here is the process or the steps that we're going to go ahead and follow for this lesson. Step 1, we'll need to determine the translations, really transformations of the graph, and we're going to have to graph the translation of 0, 0. Graph the translation of the point 0, 0. And there's a reason for this. I like to call this point, please add this to your notes, I like to call this the anchor point, your anchor point. Because no matter what else goes on with the function, that point after you translate it is not going to move. Okay, this point will not be affected by anything. Reflection, stretch, compression, doesn't matter. Number 2, for a parameter of a, we're going to draw a dashed horizontal line through the transform point, and that's going to serve as like a reference point for our stretch and compression and or reflection if we have any. If we have a parameter of 1 over b, meaning we'll have horizontal stretch or compression or reflection, we'll draw a vertical line as a reference line, and that will help us with our stretching, compressing, and reflecting. Step 3, we're going to perform any of those that we need to. So if we have to stretch or reflect or compress, we'll use our knowledge of our parent function to go ahead and plot the rest of the points. Okay, and step 4, draw a smooth curve through all the points. Okay, make sure you include arrows on both ends because they are going to keep going forever. And then we'll erase our reference line. All right. Here is the first example, and we are asked in part A to graph the function using transformations. So I need my transformations. So what I'm going to go ahead and do is I'm going to do the same step as I did kind of in the last problem. Is I'm going to identify, okay, what is my a value? And here, a is equal to -2. Okay, and that's important because that's going to cause stretch, right, by a factor of 2. I'll just put by 2. And we're going to have x-axis reflection or vertical reflection. Okay, so that's important. Our h value here is a +3. That means we're going to go to the right 3 units. And our k value is 5. So that means we're going to go up 5 units. All right. So I want to go ahead and I want to graph this function. So what I need first is I need an x and a y-axis. So I have to go ahead and plot that down. And since this function is so wide, what I want to do is I want to move like my window, what I'm looking through, where I plot my points. Now I do have a translation to the right 3 and up 5. So what I'm going to do is I'm going to move my axis over a little bit. I'm going to put my x-axis as far as my y-axis. I'm going to move my y-axis over to the left because I know I'm going to have to translate to the right. Okay. And then I'm going to move my x-axis down just a little bit, maybe here. Okay. And if you find you run out of room, you can always just go ahead. You can erase your lines and then replot. So it's not that big of a deal. Okay. So here's my x and my y-axis, and I'm going to go ahead and just label some points 1, 2, 3, maybe 1, 2, 3, just so the scale is obvious. And then I'm going to go ahead and start doing my my steps. So remember, step 1 is translate your anchor point. So 0, 0, okay? And what we do is we take 0 and we add h, and we take 0 and we add k. And that's our transformed point, right? So we already said, hey, I have to go to the right 3 values, so 1, 2, 3, and I have to go up 5. So up 1, 2, 3, 4, 5, and then here is the new anchor point. And I'll leave that in red. That's not going to move at all. Okay, and what I'm going to do is I'm going to put a dashed line through this. This is going to serve as a reference line for when I do stretch and compression. Okay, so now what I want to do is I want to go ahead and graph my next points. And going back to the parent function, which is important. Remember, the next 2 points are going to be left 1, down 1, exhibited here, and right 1, up 1, okay? So I'm going to do that first, and we'll come back to the parent function for the other ones. So here, I need to graph my next points. Left 1, down 1, left 1, down 1. However, I do have a reflection. So instead of going left 1, down 1, I'm going to go left, up, okay? That's because of a reflection. Remember, I have an x-axis reflection here. I'm also going to have to stretch by 2, so that distance, that vertical distance is going to grow by a multiplier of 2. So instead of left 1, down 1, I'm going left 1, up 1, and then left 1, up 2, right? This distance went ahead and grew by a multiple of 2. So that's how I got that point. Okay, now the next point, instead of going right 1, up 1, I'm going to go right 1, down 1, and right 1, down 2. Okay, that's because of my reflection, and again, because of my stretch. All right, so there's the next point. Okay, now let's go ahead and I'm going to go back to the parent function. Sorry, I hope I'm not making you sick with all of this movement. But the next points on my parent function are -8, -2, and +8, +2. So I'm going to go ahead and go back. Okay. And I'm going to go to the left 8. 1, 2, 3, 4, 5, 6, 7, 8. And then instead of going down 2, I'm going to go up 2. And instead of up 2, I'm going to multiply that by 2. So it's up 4. Up 1, 2, 3, 4. Okay. I'm going to do the same thing on the right side. I go right 8. 1, 2, 3, 4, 5, 6, 7, 8. And normally I go up 2, but this case, because of my reflection, I'm going to go down 2. 1, 2. And that distance has to grow by a factor of 2. So I'm going to multiply that. 2 times 2 is 4. So down 1, 2, 3, 4. Okay, and I get that point. So let me go ahead. I'm just going to erase that real quick. And then the last step, I'm going to draw a smooth curve through these points. I'm going to try my best to do this. And there you go. So there is your transformed function. Now, a good way to check and see, did I actually do it right? Well, look at this function. Does it look like a cubic root function? Yes, it does. It looks like that weird squirmy S. If you end up with something that looks like it's like been bouncing around, then you know you made an error, okay? So it should have that smooth curve, so double check that. Now also ask yourself, based upon the transformations, does it look like my function has a reflection? Yeah, it does. It has that vertical reflection. Okay, and then did I go ahead and stretch by factor 2? Well, yeah, it does look like it's been elongated. And it's definitely been translated, right, to the right 3 and up 5. So that's kind of how you can go ahead and check. Now, the last steps, remember, make sure you erase your reference lines here. Those aren't actually part of the graph. We're just using them to help with our stretch and compression. Common question, do I have to include that reference line? Like if I don't need it? Answer is no, you don't have to draw that and then erase it. But it kind of helps with that stretch factor and the reflection, gives you a sense of reference. You may also be asking yourself, hey, like I stretched and reflected all my points, but why didn't I translate them? Well, that translation takes place when you translate your central point here, the 0, 0. So then you don't have to translate anything else. You're working off of that central anchor point. Okay, that was part A. Part B, they want us to go ahead and state the domain and the range using set and interval notation. And that's really easy because our domain is all real values. So x values such that -infinity is less than x, which is less than infinity. And then in set notation, it's -infinity to infinity. Range, again, the same. It's your y values from -infinity to infinity. So negative infinity is less than y, which is less than infinity. Common error here is people will substitute in x's when they're talking about the range. Remember, range is your y values. Okay, and end behavior. Part C, they want you to state the end behavior. So I need to go ahead and state the end behavior. You know what I like to do? Here's a little trick for end behavior. I like to go to my end behaviors and I use left, right, or up, down. So I'm looking at this end. Hey, this is the left side and it's going up. So in terms of math, that is as x goes to, well, the left is negative infinity if you go forever. Okay, and then your function here, g of x, your y values, well, going up, you're going to go towards positive infinity. Okay, you don't have to include the positive if you don't want to, but just a note there. Okay, how about the right side? So over here, it's to the right, and my function is going down. So that is as x goes to positive infinity, right? That's the right. My function is decreasing, going to negative infinity. All right, that is the first example. Again, what we did was we identified our transformations and we graphed the parent function with these transformations, moved the anchor point, and then applied any stretch or reflection or compression. And then what we did is identified the domain, range, and the end behavior. I do have a practice problem for you here. Please go ahead. I want you to pause the video, try these, and then I'm going to ask you some questions here in the Ed Puzzle if you're watching the Ed Puzzle. So try these and then I'll show you the example. All right, hopefully you have went ahead and graphed this, and then did you state the domain and the range and the end behavior? So here is your function. We had vertical compression by a factor of 1/2. And we translated to the left 2 and down 3. You don't have to state those, but that kind of helps knowing what you're doing. End behavior, let me scroll up a little bit right there. Okay, so your end behavior is like the parent function. As x goes to negative infinity, the functions are going down. And then as your x values increase, your function values are going to increase. Slowly, but surely. Okay. All right, here is the next example. And this example is similar to the last one. They want us to graph the function using transformations, state the domain and the range using set and interval notation, and then we'll state the end behavior. Okay, so in this example, we have a 1 over b value, and our 1 over b value is -2. So this implies, if I go ahead and take the reciprocal, that b is equal to -1/2. It's going to be horizontal compression, also with a reflection. Our h value in this case is going to be a +1, so we'll go to the right one. And it looks like our k value is a +3, so we're going to be moving up 3 units. All right, so since I'm moving to the right one and I'm moving up 3, I'm going to adjust my axis. Not much. So here's my y-axis and my x-axis. I'm moving up 3, so I'm going to shift my axis down a little bit. Okay, so there's my x and my y-axis, and again, I'll go ahead and scale my graph 1, 2, 3, 1, 2, 3, and then I'm gonna translate my central anchor point. Okay, and again, I'll put this in red just so it kind of sticks out. So I'm going from 0, 0, I'm going right 1, and then up 3. So there's my central anchor point. Okay, and then I'm going to plot my next points. So remember, -1, -1, and left 1 is left 1, down 1, and then 1, 1 is right 1, up 1. And since I'm having some horizontal stretch and compression, what I'm going to do is I'm going to put in a reference line. Again, you don't have to put in this reference line. We're going to erase it, but that just gives me a reference for where I'm reflecting about. Okay, all right, so my next point, I'm going to go left 1 and down 1. Okay, left 1 and down 1. But instead of going left, I have to go ahead, I'm going to go right because I'm reflecting. So right 1, down 1. And then instead of going right 1, I have a horizontal compression by a factor of 1/2. So that's going to be right 1/2, down 1. So right here. Okay, now I'm going to do the second anchor point. So right 1, up 1. Instead of going right, I'm going to go left. And instead of going right 1, I'm going to go right 1/2, right? Because I have horizontal compression. So right 1/2, up 1. And really these should mirror each other, right? Over that central anchor point. Okay, now I'm going to go ahead and do the outer two most points. So left 8, down 2. Okay, so instead of going left, I have to go right. So I'm going to go right 1, 2, 3, 4, 5, 6, 7, 8. And instead of going actually 8, I have to cut that in half. So I'm only going to go right 4. 1, 2, 3, 4. And I'm going to go down 2. 1, 2. Okay, same idea for the last anchor point to the right. Positive 8, comma 2. I'm going right 8, up 2. So this time I'm going to navigate left instead of right because I have the reflection. And then instead of going left 8, I'm going to go only left 4. 1, 2, 3, 4. And that's due to my horizontal compression. Up 1, 2. Okay, so there are all my points. And again, I'm going to go ahead and draw a smooth curve or attempt to. Let's see. Got them. Throw on some arrows at the end. I'm going to erase my reference line. I should be commissioned for this art piece. It is that good. Last point. I'm going to go ahead and state the domain and range. This is part B. What is the domain? Again, I'm going from negative infinity all the way to infinity. That's all real values. So don't forget both set and interval. So this is set, just in case you forgot. Right, which is really like inequality. That's interval. And then range is the same. So from negative infinity to infinity. And beyond. Negative infinity to infinity. Okay, last part, part C. What is the end behavior of this function? So again, just using the quick annotations, this is going to the left and it's going up. So that's as x goes to negative infinity. What is our function g of x doing? It is increasing towards positive infinity. And then over here, this function is going to the right and it's going down. So that is as x approaches positive infinity, g of x approaches negative infinity. All right, that is it for that example. I do have one last example for you guys. Please pause the video, identify your transformations, go ahead and graph, and then don't forget, state your domain range and the end behavior. Okay, hopefully you have paused the video and tried that example. Here is the solution. All right, that is going to do it for this example. Hopefully you learned how to graph cube root functions via transformations, and I will catch you next time. Be safe, be easy. Peace.